Hello, in this video we will solve separable equations. Separable differential equations have the format dy dx equals mx over ny. This could also be rewritten into mx times p of y, where p of y is 1 over n of y. The key is that the variables can be separated. Whether it's division or multiplication. So it's in the name, separable equations, separable variables. Separable differential equations are sometimes written in the following format. If you moved n of y over and then moved m of x over, you'd end up with the following. This format is a bit more similar to the format used in solving linear first-order differential equations in the last video. Again, it's similar, though, in that notice we have only y's in terms of the function that's multiplied by dy dx, and we have only x in terms of the function that is subtracted. So again, the variables can be separated. Okay, so how do we go through and solve? How do we solve separable differential equations? Let's look at an example. This example will inspire the method. So let's say we have dy dx equals x squared over 1 minus y squared. Okay, if so, we could move the 1 minus y squared over to the other side. Okay, so if you did that, one thing that you might notice if you spend a lot of time staring at it is that the left-hand side here has the form of a chain rule derivative from Calc 1. So let's look at that a bit more formally off to the side, and then you can kind of see the pattern, right? So if we go back to Calc 1, calculate the derivative with respect to x of a function of y, what we end up doing is we use the chain rule. So we take the derivative of the function of y with respect to y, and we multiply it by dy dx. So you may not have seen it written exactly in this format, but the chain rule is you take the derivative of the outer function here, which is the f, right? And when you do that, you take it you take the derivative with respect to the variable it's in terms of, and then you take the derivative of the inner function. So this is the derivative of the inner function. This is the derivative of the outer function. Okay, so hopefully that matches more precisely with how you recall the chain rule. Okay, and then this outer derivative we could actually just shorthand into f prime of y dy dx. The prime notation, it's implied that you're differentiating with respect to the variable that the function is in terms of. Okay, so look at that. Look at the far right here. So notice how we have derivative of y dy dx, and then we have something that looks kind of like that. We have some y stuff dy dx, y stuff dy dx. Okay, so What we would like to do is we would like to be able to go through and reverse this process and go from right to left. We'd like to be able to go through and rewrite this as the derivative with respect to x of a function. Why is that? Because we have x stuff on the right-hand side. If we have x stuff on both sides, then it will just make things simpler. Or another way of saying it is you'll see. All right, so in terms of the right hand, let's start off on the right. So let's say we have 1 minus y squared dy dx, right? That's our function here on the left. And then if we're reversing this, okay, so the dy dx doesn't change. And then here, what we want is we want the thing that we would differentiate to get 1 minus y squared. That's another way of saying that we want the antiderivative. So the antiderivative of 1 minus y squared is going to be y minus y cubed over 3. Okay. And then from there, we could jump, we could back one more step and say this is the derivative with respect to x of y minus y cubed over 3. Okay, so we're taking what's on the left here. We're starting it in this format because this is what it looks like. And then we're just going back to the left where we're kind of reversing the chain rule process. All right, and so if we do that, we end up with the derivative with respect to x of y minus y cubed over 3. And then we could go through and rewrite the right-hand side to also be a derivative with respect to x. That would be x cubed over 3. And if we did that, now you can see how we, on both sides now we have derivatives with respect to x. So we can integrate both sides with respect to x. And then if we do that, oops, I forgot my x's, the x's. Now, if we do that, it's important to understand what's going on here. So you're calculating the antiderivative of a derivative, okay, with respect to the same variable here. So the variables match. So you're calculating the antiderivative of a derivative with respect to x with respect to x. If you're to find an antiderivative of a derivative, those two are going to end up canceling each other out. The antiderivative of a derivative is the original function. So we're going to end up with y minus y cubed over 3. And on this side, we're going to end up with x cubed over 3. And then we put in a plus c to represent the constant that could have been gone away when we differentiated, and then move the x cubed over. So we get y minus y cubed over 3 minus x cubed over 3 equals c. Okay, and this answer looks different than answers from previous sections. That's because it's an implicit solution. So that frequently happens with problems that have a format similar to this, is that we end up with implicit solutions. We'll do a later example where we go through and we take the implicit solution and try and get to an explicit solution, but that's not strictly necessary. An implicit solution is a solution to a differential equation. So this thing here, if we went through and plugged it into this original equation, it would solve the original equation. It would make the original equation true, just like it would if we had y by itself, which is what we had in previous examples. Okay, so this process that we went through here, this process is very formal. It's ironclad. All right, so it's guaranteed that everything that we did here, it's crystal clear that it does work, that there's nothing shady to it. All right, we went through and rewrote. We can move the 1 minus y squared over. We can go through and we can do this to turn the left-hand side into the derivative of something. We can do the same thing to the right-hand side. We can integrate a derivative, and then the integral and derivative cancel, and we get to the original functions. Okay, everything is very formal. Everything is very definition-based. So this proves that the technique works. However, and so I want to be crystal clear about this. This is not how you actually go through and solve separable equations. You would never see anyone solve a separable equation like this. If you've watched other videos on separable equations, you may not have seen anything that looks like this. And so you might be wondering why do this? Well, it's just because we want to be certain that the method works before we go through and solve it in an informal setting. All right, so let me show you the informal version. The informal version is surprisingly simple, and it's why it's the way that we solve differential equations, separable differential equations. So if we have dy dx equals x squared over 1 minus y squared, we can go through and we can move the 1 minus y squared to the left side, and we can move the dx to the right side, and you're left with 1 minus y squared dy equals x squared dx. And at that point, we're just going to add integral symbols on both sides. The antiderivative on the left is y minus y cubed over 3. The antiderivative on the right is x cubed over 3. Add a plus c, move the x cubed over, and you can see we get the same answer. Now, this is very informal. You'll notice that I just added integral symbols on both sides. I've got dy on one side, dx on the other. Can you go through and do that? Yes, you can. How do we know? Because of the previous step, because we went through and solved this in a formal setting and showed that that technique does work. Okay, so it is okay to go through and use this method because we've proven it previously in the previous example. Okay, so the next thing that we want to do, so this is how you solve separable equations. This is the technique right here. So the next thing that we want to do is we want to go through and generalize this method. We want to come up with a set of steps that would work for any function, because a question you might have is, well, was there something particular to this problem, to that setup that made it so that we could go through and solve the separable differential equation? Okay, so let's generalize this. All right, so suppose we have dy dx equals mx over ny. Then we can always go through and move the ny over. Dy dx equals mx. Then we can go through and we can define, right? So we can define h1 of x such that the derivative of h1 of x equals m of x. And we can define h2 of x, h2 of y, such that the derivative with respect to x of h2 of y equals, now here we're going to use the chain rule, right? So the derivative with respect to y of h2 of y dy dx, which equals h2 prime of y. Oh, hold on. Which equals n of y dy dx. All right, so we're going to go through and we're going to pick h1 of x such that if we took the derivative of h1 of x, we got m of x. That's another way of saying that h1 of x is the antiderivative of m of x. And we're going to go through and define h2 of y such that if we took the derivative of h2 of y, we would end up using the chain rule. We'd get the derivative with respect to y of h2 of y dy dx. And then this is another way of saying that h2 of y is an antiderivative of n of y. Okay, so what we're doing is we're finding the antiderivative of m of x, and that's h1 of x, and we're finding the antiderivative of n of y, and that's h2 of y. And that enables us to rewrite this as the derivative with respect to x of h1 of x, and to rewrite this side as the derivative with respect to x of h2 of y. Then we can go through and we can integrate both sides. Oops, almost did it again. With respect to x, that's an little important detail there. And the derivative with respect to x of h1 of x with respect to x. And again, if you integrate, if you find the antiderivative of a derivative, the antiderivative of a derivative is going to be the function itself. And then the antiderivative of a derivative is the function itself plus c, and we get h2 of y minus h1 of x equals c. So this is the exact same steps that we used previously. However, it's just used with generic functions, m of x and n of y, and then we get into generic antiderivatives, h1 of x and h2 of y. But other than that, it's the exact same steps that we did earlier. And it just shows that we could go through and do this with any m of x and n of y, that it doesn't matter what x function we have in the numerator and what y function we have in the denominator, if we can go through and separate the variables so that we have x's on top and n's on the y on the and y's on the bottom, then we can go through and use the following steps. Okay, so this is the formal version of the proof. This proves that we could go through and write out all this formal stuff every time. Is there an informal version, right? So certainly, right? So we want to be able to go through and use our informal steps. So if we had dy dx equals m of x, n of y, okay, we could go through and we could move the y's over and the x's over, and we'd get n of y dy equals m of x dx. And then we could just throw in integral symbols, just toss them in here, all right? And then we could go ahead and say, let h1 of x be the antiderivative of m of x, right? In other words, h1 of x is the function that we would differentiate that would get us m of x. So in other words, the derivative with respect to x of h1 of x equals m of x. And then we could go through and say, let h2 of y be the antiderivative of n of y. In other words, the derivative with respect to y of h2 of y equals n of y, or the derivative with respect to x of h2 of y would equal n of y times dy dx. Right? So if you get to here and h1 is the antiderivative of m, then that's also means also this. And h2 is the antiderivative of n of y. That means the same thing as this or this. You can see these two definitions. Look at those. Those are the same definitions that we used here, right? So I have not changed the definition. It's still the same definitions. It's just that in the context of this one, we were thinking about what would we differentiate to get from here to here. And in this case, we're thinking about it in terms of the antiderivative instead. And that's two sides of the same coin. All right. This enables us to go through and say if h2 of y is the antiderivative of n of y, then on the left side, we're going to get h2 of y. And if h1 of x is the antiderivative of m of x, then we're going to get h1 of x on the right-hand side plus c, and we end up getting to the same place using our informal set of steps here. Okay, so this goes through and proves that the informal set of steps end up getting us the same answer with the same, where we end up using the same conditions throughout. And so we can go through and replace our formal set of steps here, with our informal set of steps. And this basically justifies the simpler technique for going through and solving for separable equations. Now, you could every time go through and just do it this way. But that's not how people do it. That's not practical. Instead, what you'll see whenever you see people solve separable equations is they go through and they use these steps here. All right, so that is what we are going to do throughout the rest of this video. Okay, so let's look at an example. We have dy dx equals 3x squared plus 4y, plus 4x. It'd be a shame if the first example was not separable. Plus 2 all over 2 times y minus 1. And we also have an initial condition, y of 0 equals -1. Okay, so first, your first step is this separable? You'll notice if you can separate the x's and the y's, then it is separable, right? And so you'll notice you've got x's in the numerator and we've got y's in the denominator. So from here we can go through and we can move the 2y minus 1 to the left, and we can move the dx to the right. And then we can just toss in some integral symbols. Yeah, and we've proven that that's okay, that you can do that. And then from there, we go through and find the antiderivative on the left. So we're going to get 2 times y squared over 2 minus y. And then the antiderivative on the right, we're going to get x to the third plus 2x squared plus 2x. Put in a plus c. We can multiply that 2 back through. We get y squared minus 2y equals x cubed plus 2x squared plus 2x plus c. So at this point in the previous example and in our proof, we went through and we moved the x's over to the left-hand side and ended up with getting a bunch of x and y stuff equal to c. That's completely legitimate. That is fine. However, right, in this case, we've got this initial condition, and that's going to enable us to go through and get rid of the c. And I'm taking a look and I'm noticing that my y function here on the left-hand side it's very easy to solve for y. It's very easy to go through and get y by itself. So this here is the implicit solution. Right? And again, the implicit solution, I didn't mention this earlier actually. The implicit solution, if you're not familiar with the terminology, so implicit just implies that y is not by itself. All right, so it implies that we don't just have a bunch of x stuff and that's our answer. Instead, our solution is both x stuff and y stuff all mixed together. The solution is implicitly in there. As opposed to explicit. Explicit is when you have y by itself and it's very clear, right, what the solution is. It's defined with just a bunch of x's, x stuff. Okay, so implicit mix of x's and y's for the solution. Explicit, you have y by itself and you just have x's. Okay, so in this case, this is an implicit solution. What if we wanted to go through and find the explicit solution? In this case, it's very easy to do that. So I'm going to go ahead and do that. So rather than move the x's over and just get a bunch of x's and y's equal to c and call it a day, instead, we're going to go through and we're going to see if we can find the explicit solution. So to do that, we need to get y by itself. So how do you get y by itself? So if you've got something that's of this form and you want to get y by itself, you need to complete the square. Right? So completing the square, you take the coefficient of y, -2 over 2, square it, you get 1. So it tells you have to add 1 to both sides. I'm just going to put the 1 inside that c, okay? And then the left-hand side here, we can go through and rewrite this. This is y minus 1 squared equals x cubed plus 2x squared plus 2x plus c. And then I can go through and take the square root of both sides. So we're going to have plus or minus the square root. x cubed plus 2x squared plus 2x plus c. And then I can move the 1 over, and I get y equals 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus c. And so now notice I've got y by itself, and I have on my right-hand side here, I've got a function that has c in it. So I can now use my initial condition to solve for the c. However, I want to point out one other thing. So notice how we have this plus or minus, right? So the solution to our differential equation, right, should, assuming we're going to use the explicit form, it needs to actually be a function. Okay, so we can't have a plus or minus, and we need to be able to go through and get rid of the plus or minus. And the initial condition will enable us to go through and do that so that we end up with a function that does, pass the vertical line test, that is a function. All right, so how do you do that? So you can go through and you can calculate what y of 0 is. That's going to give you 1 plus or minus the square root, right? And if you plug in 0, you get 0 for all these. So you're just going to end up with the square root of c. And then we know y of 0 is -1. So we're going to have -1 equals 1 plus or minus the square root of c. This is saying that -2 equals plus or minus the square root of c. Now, if you think about this logically, can -2 equal positive the square root of c? No. All right, so our solution for this initial condition, again, it's for this initial condition. A different initial condition might cause us to use the plus solution. All right, so but with this initial condition, the initial condition prohibits the plus. And so we can just get rid of it. And so we're going to have -2 equals negative root c, and then c is going to equal 4. Now taking that and plugging that in along with this, this discovery that we've made as we went through and solved for it, enables us to get y equals 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. So to recap here, you go through and you solve this differential equation. This is the solution that we found. This solution here, this is, or this, or any of these solutions here, anything starting here and downward is an implicitly defined solution until we get to here. This is explicit because we've got y by itself. However, it has multiple solutions. And so, and it still has the c. And so we can use the initial condition to get rid of the extra solutions and to solve for c. Okay, so that's the method. That's how to go through and solve, put your solution into the explicit format. Let's do one more quick example. So we have dy dx equals 4x minus x squared over 4 plus y squared. All right, so just again, the variables are separated. We have x's and y's that are not together. So we can go ahead and move the y's over to the left-hand side. And we can move the x's over to the right-hand side. And then we can just throw in some integral symbols. And the antiderivative on the left is 4y plus y cubed over 3. And the antiderivative on the right is 2x squared minus x cubed over 3. And then we add in a plus c. And that's the end. It's that simple, right? If we were to add an initial condition, so you could add an initial condition to this. So like, let's say that you went through and solved, well, let's not think of it in terms of initial condition. Let's say you had this, you went through and you solved it, and then you go through and you want to find a solution that corresponds to a particular point. So let's say I want to find the solution that passes through zero comma 1, right? So the thing that I want to focus on here is that if you go through and you solve this differential equation, it's just like the differential equations that we solved previously, in that if you were to go through and graph this, this generates an infinite number of solutions that goes through just about every point. And so if you're looking for a specific solution, one solution, what you need to do is you need to have a point that lies on that solution. And so if you have this as your solution and you want to find a solution that passes through a particular point, you can just take that point, plug it in, solve for C, and it will give you the solution that actually passes through that point. Okay, so I wanted just to make that clear that it doesn't have to be thought of in terms of an initial condition so much as you solve a differential equation and you get a family of solutions, and then you say, how do I pick one? What if I want just one? Well, you could just use a point to get yourself just one. Okay, and so if that were the case here, you could, this is what this is saying, is this is saying that x equals 1, x equals 1, x equals 0, y equals 1, and then you just take that and plug it in, and we would end up with 4 plus 1/3 equals C, and then 12/3 plus 1/3 equals C, 13/3 equals C, and then 4y, and then our solution would become 4y plus y cubed over 3, and then if we moved everything to the one side, we'd have minus 2x squared plus x cubed over 3 equals, I can't even read my own handwriting, 13/3. And that would end up being the implicit solution that passes through the point 0 comma 1. Okay, so that is the video on separable equations. Thank you for watching. See you next time.